I think it's going to take getting a ladder in here and adjusting it. By the way, I made that mount up there for the projector. That should be impressed. The education lottery. So chapter 5. Let's get into chapter 5, and we're working on this. This allow you to get through with. Let me get out of this. To get through with the first labs that are required, and make sure we go over the lab procedures. Don't let me go too far on this. And we're getting there, guys. We're going to be doing hands-on lab before long. Oops, I'm getting close. Okay. So what we're going to do is get into the basic rules of line diagrams. We're going to look at the 3 sections of most line diagrams, and then, of course, this is where we're going to get into our logic functions. So what we got to understand the difference between a rung and a line. A line is anything that moves horizontal. So a rung consists of one or more lines. What does this rule right here say? One load per line. Not per rung, per line. Y'all understand that? So I could come up here and do this. This would still be one rung, but it would have 2 lines. So I could come up and do this. Oops, sorry. I got my cord. So I could come up here and do this, drop this down and put, let's say we put a relay down here. This is a line and this is a line. So this moves horizontal, so this is another line. You don't understand? So this rung would have 2 lines. But I can only put 1 load per line. So if I come up and do this, that's bad. Because what happens now is your voltage is divided across those loads. So neither one of the loads get the voltage that they're supposed to have. But remember, power varies with the square. So if those 2 loads had exactly the same opposition, and this was a 26 volt control circuit, then each one of those guys would only get 13 volts, and they would produce 1/4 of the power, and that wouldn't, the solenoid wouldn't have enough power to pull it in, and the relay wouldn't have enough power to pull it in either. Right, you understand? So how many loads per line? 1 load per line. But we can have a multiple line rung. Everybody understand the difference? So how many loads can we have per rung? A lot. But we can only have 1 load per line. Loads must be connected in parallel. So now we got a parallel circuit. Loads must be connected in parallel when more than 1 load must be connected in the line diagram. For this we have 2 lines. So this rung has 2 lines. Everybody okay? You understand the difference? Control relays, solenoids, and pallet lights are loads that are connected directly or indirectly to L2. So we got to connect them. So normally what we do is we connect one side to L2, and the other side is going to be fed by our control devices. So what's going to be between L1 and the load is going to be control devices. and there's nothing going to be between L2 and the load unless it is a magnetic motor starter. The only thing you'll ever see over here is overloads. And that identifies the relay as a magnetic motor starter. So if it's not a magnetic motor starter, there's not going to be anything between L2 and the load, right? Everybody okay? Yes or no? And if we need multiple loads in the same run, we hook them in parallel, which means it's going to add multiple lines. So this run right here would have 3 lines in it. So here we go. Magnetic motor starter coils are connected to L2 through normally closed overload contacts. Now these are not the overloads. The overload consists of 2 things. It consists of a sensor that senses the motor current, and then it has a contact that's controlled by that sensor. So what goes in the ladder diagram is not the sensor, it's the contact that the sensor's controls. Does that make sense? And they're going to be normally closed. So as long as we don't have an overload on our motor, these guys are going to connect L2 to the load. If an overload exists, that means the motor, if it's running, it's going to click that line out, right? It's going to remove power from the coil. And then, normally these overloads are not auto reset. These external overloads, they do not auto reset. You're going to have to push a button on them to reset. So if I don't... So here's a magnetic motor starter. And this is pretty neat because you can see the auxiliary contact on it real easy. Contacts on it because this only runs a quarter horsepower motor. So this is a motor starter. So here's L1, L2, L3. So this is where the power comes in, right? Down here we have T1, T2, T3. Can you see the way this works? So what they do is they go ahead and wire it up, and this is a terminal board. But on the terminal board, what they do is put banana plugs. The labeling on the terminal board is exactly the same as the labeling on the contactor. So that means, but instead of hooking directly to the contactor, we still bring in so the thing that comes in on the top still does what? Comes in on the top, and what comes in on the bottom still comes under the bottom, but instead of us opening up these screws right here, these compression nuts, and putting the wire under there, and what happens? How long would these things last? Why? Because people don't know. People will strip them out, they'll cross-thread them, they'll screw them up, and believe me, originally, when I took the motor controls class here, all our relays was laid out on a table. And we wired them up. And we got rid of that real fast when I got here. First of all, we had that one designed, and then we had this one designed. So, and this has really, really worked out well. They've lasted a long time. So here's my overloads. So these are not the overloads. These are the sensors. Okay. So what happens is T1 or T3 is connected to the sensor. The sensor goes out to T3 down here, which is where we connect our motor. So all the motor current flows through this sensor. And then it's got a set of contacts that we'd have to find. They're right down here. That these are the overload contacts right here. So if this guy here senses an overload, it opens that contact, and of course this goes back up to the relay. Y'all understand that? And then I have this big button right here. What's this big button right here do? Yeah. Well, one thing, the new overloads has to have a trip indicator, so this right here will turn red, indicating it's what? Trip. And then after the overload cools down, then you can do what? You can reset it. So if you're there when it trips, you can hit this and it's not going to do anything because that overload's got to do what? It's got to cool down. It's kind of like a circuit breaker. So if you're standing right by a circuit breaker when it pops, then odds are you can't do what? You're going to have to wait till it cools down, because circuit breakers operate off heat also. And we'll look at a little more detail how these overloads work. It's really, really neat. But we have one button to reset it. The old ones have multiple buttons on it. And then finally, OSHA finally took control of it and said we need one reset button that resets all the 3 overloads inside there. In fact, on your new ones, you only have one contact. That if any overload trips, it trips this one contact, right? You understand? The old ones, you had one contact per overload. So if you see a diagram that's got one contact, that would be one like this. If it's got 3 contacts out, then it would be the old one. Originally, they only sensed L1 and L2 because they had in their mind that if you have that all the current would go through L1 or L2, even if L1 or L3. That's it. So originally we tripped L1 and L3, and they didn't sense L2. Well, they found out that was wrong real fast. So you might run into an old magnetic starter out there that's got 2 reset buttons on it, and it's only going to be on L1 and L3. If you ever replace it, you need to go into these guys, because they found out that L2 could overload and not affect the other 2, by the way. So this is a magnetic motor starter. Here's the auxiliary contact strung on the side. Here you can actually see this. Here's the force button right here, or the manual override. Okay, I think this book calls these guys press to test. Normally when we're in the field, they're going to call it an override. And you can actually see the operator. So you can see it working right here. So we can come in, and these are somebody help me out. Yeah, these are not screws, but normally these are screws right here that you could actually put more. No, the thing that mounts it right here. These are golly, I know the name as sure as my rivets. So this is actually riveted on here. Okay. So normally these would be the holes so you could mount multiple contacts, and then the next one would operate off of this, right? Y'all see that? So these are our magnetic motor starters. This is a little different. This has 4 main contacts. We only need 3. So this gives us the ability to use this as an auxiliary contact right here too. So it's a little different. So what we do is we draw the symbol. So normally ours would look like this. It could look like this for 3-phase, or it could look like this if it's a single-phase motor where we look at both lines. It's a bad habit, and you have to be really careful about some of your HVAC systems. So normally if we got a single-phase motor, the best thing to do is we got 2 lines coming down, right? Okay. So let's say this is a 240 volt motor. What we like to do is we like to break both lines, because that way, if this line breaks and this guy stays open, then that motor is electrically hot. You can get your butt zapped by getting the ground. Unfortunately, if I was in a place called U.S. Steel, I would have to double break a 240 volt motor. Residential lives under their own rules. So you get by a lot in residential. National Electrical Code lets you get back a lot in residential that we don't. So this is the main compressor contactor for a house unit. So this is a contactor, and this is what they do on the thing. So if you work on a house unit, you need to be real careful, because they don't double break the 240 lines. Industrial application, and this is legal, by the way. So notice this side comes what? Comes straight through, and they only break one side. So here's the contact right here. So on a house unit, they only usually break one side. So that means this side, and it's 240. So that means you got 120 volts to ground on the 240 side. If you get between Any 240 in ground, that's 120 volts. So be careful when you work on these. So this is for a watt. This is the compressor relay contactor for a HVA system. So be careful you work on those with power on. Of course, you need to guard these poles too, right? So this would be a high voltage this would be for a high voltage single phase motor. Now this would be for a single phase motor. This would be for a 3-phase motor with 3 overloads. This would be what we'll use for our contact, because we got one contact, right? You understand? That's what? That's controlled by 3 overloads. Are we okay? Yes or no? So the only thing allowed, the only device that's allowed, there is no 2 loads. So these normally closed overload contacts are not loads, they are devices. The only device allowed between L2 and the load are overload contacts. And they only belong to motor starters. You okay? Any questions? Control devices are connected between L1 and the load. So all our control devices go in. Now, how many control devices can we put in a line? A lot. Right? You understand? We can put them in parallel, we can put them in series. So the control devices are not what we're concerned with. We can only put 1 load per line, or we can put a lot of control devices. What we call the decision-making section of the circuit. And how you hook the control devices does not make it a parallel circuit. It does not make it a series circuit. Now, when we talk about parallel and series circuits, we are talking about the what? The loads. So let's see any symbols we don't. This guy right here, notice this is a float switch, but they cut off one side. They don't cut it off. They cut it off and draw a line across. What's this a symbol for? Pressure switch. This is a normally open limit switch. This is a symbol for a momentary contact pushback. What do they put on L1 indicating I have a connection right here? They put a dot. So if you don't put a dot there, it's up to you. I'll take points off. And don't say so and so. Let me get by with it. By the way, about the 3rd, 4th week in the semester is when the campus police start checking little things. So you need to make sure you have your. What this brought up, I forgot all about this, but we had a big group of Toyota training over in the Millside building yesterday. And campus police came over there and wrote them all tickets for not having their parking decal on it. Of course, they got out of it because they're not students; they were off campus. And they gave them and everybody has their own little quirks, right? So. For some reason, there is a law in the state of Alabama that says you are not supposed to back into a parking space. And they will give you a ticket. So don't back into parking spaces. Or pull through. Like we have double parking line and pull through. If your headlights are parking out of the space, you will get a ticket in Boston State. Unless you ride a motorcycle, they let you get by with it on a motorcycle. But motorcycles don't have reverse. Well, not all of them. I think some of the big Gold Wings. You can give some of the big Honda Gold Wings, and they might. I think some of those have got reverse on it. So when I rode my bike, they never gave me a ticket. I always backed in or pull through. Multiple control devices may be connected in series or parallel to control a load or a contact. So we pick up a new symbol. We looked at the temperature switch, but what is this a symbol for? When I say this, I need to circle it for you, right? So we're constantly adding to our symbols. So that's what switch? Flow switch. And most of the symbols basically have a good float's pretty easy. Pressure is a little different because it's got that half semicircle line here. We already looked at this guy. This is a what? Temperature switch. This is a foot switch. This is a pressure switch. This is a relay coil, but it's a magnetic motor starter coil. How do I know it's a motor starter? Because the overload's right there. So we can hook control devices in series. We can hook them in parallel. We can hook them in series parallel. So the control devices don't make any difference how many you put per line, right? You understand? How many you put in parallel really has no bearing on the circuit at all because these are control devices. It's those loads you got to watch out for. Because control devices produce no electrical power. They drop all the voltage when they're open and drop no voltage when they're closed. Unless they're solid state. We'll talk about that later on. Now this is what we're doing. What we have to do is, number one, is we have to make these things easy to read. So what we do on the left-hand side of L1, we assign line numbers. Not rung numbers, line numbers. So this right here is a rung, and this is where it splits up on PLCs a little bit. PLCs don't know line numbers, they know rung numbers. But what we have to have the ability to do is find things. So instead of me, okay, everybody look at this diagram, let's look up the fifth rung from the bottom, right? And I go up here, or I can say, okay, everybody look at line number 5. You look on the left-hand side, you find line 5, and you know exactly what I'm talking about. And I don't have to say the third from the bottom. I don't have to do anything. Everybody look at the contact in line number 5, right? You understand that? So this is what we do to help us identify the location of places. So line numbers go on the left. They go on L1. They go to the left of L1. And basically they're sequential. We start at some number at the top depending on where we're at, and we number sequentially. And we're going to look at a US Steel. So we're looking at what the book teaches, and then we're going to look at a true line diagram that came to us from US Steel. And they do it a little different because these line diagrams, you can't fit the whole diagram on one page. So they split this whole ladder diagram up to pages. So what they do is they start off with a page number like 138-1. Okay, so the 138 would be what? The line number would be the page number that you're on, and then the 1 would still be the line number. That is basically exactly the same. It's still within. Everybody okay? Any questions?
I got one. So you said that control device produces no electrical power.
That's right.
So you drop voltage when it's open?
Yeah, well, what happens? So what do we take to get a voltage drop? What's required to get a voltage drop? V is equal to what? V is equal to I times opposition. Now, of course, you learned R, but there's different types of opposition. Okay. So what happens, and let's just draw resistors right here. Okay, some more resistors. We'll put 4 of them right here. And then I'm going to come back to a voltage source. And let's say it's, 1, 2, 3, 4. Let's say it's 20 volts, and they're all the same size. They're all 1K, so they'll all drop the same voltage. So if they're all the same size, they drop the same voltage, and all the voltage has to be dropped within a circuit. So I've got 20 volts, so that means I got 4 of them. So that means each one of these would drop 5 volts. Because they have R, They have I flowing through them, right? You understand that? And they have ohms. Okay, so what would happen if that guy right there opens? How much voltage would this guy right here drop? Huh? How much would it drop? It would drop 0 volts. As soon as that resistor right there opens, I lose I. If I lose I, then V is equal to I times R. Okay, so let's say 50,000 ohms. Well, 0 times 50,000 ohms is how many volts? So it drops no volts. Okay, so if it drops no volts, that means I would come over here, if I measured relative to common right here, if I measured relative to common, if I call this common, if I measured on this side, I would have 20 volts. What would I have if I measured on that side? I'd have 20 volts. It drops no volts. There is no I. If there's no I, there's no what? I don't care how big the resistor is. If you have no I, you have no V. Okay, you understand? How much voltage would this second resistor drop? I'm sorry, how much voltage would this guy here drop? How much voltage would it drop? It would drop none. So it means dropping 0 volts. So if this is my common, this is 0. So that means if I come over here and put my voltmeter right there, it's going to measure 0 volts. If I put my voltmeter right there, it's going to measure 0 volts. If I come over here and measure this one, how much voltage is it going to drop? 0. So that means if I've got 0 volts right there, I've got 0 volts right there. I got 20 volts right there. I got 0 volts right there. So if I measure across the open, I measure the applied voltage. How much work is being done? None. So we don't really say, people say it's dropped across the open. I like to say it appears across the open because it's not dropping a voltage because there's no current flow. So if we've got an open in a series circuit, the entire voltage appears across the open. And basically that's a big point on troubleshooting. So what we do is we clamp on, put our common on L2, and we start moving across things. And if I go across the coil, I got 0 volts on this side, 0 volts on that side. That means that coil is not open, right? Because if it was open, it would do what? It would drop the entire voltage. Okay, y'all understand that? So if something's in series, if it's open, it drops the entire voltage. So if I went back to these lights right here, if I measured across the light switch for these lights right here, it would measure 0 volts. Because it has 0 ohms. If it's got 0 ohms, we got the same problem. So if I've got 5 amps, well 5 times 0 ohms still gives me what? 0 volts. But if I open that light switch, this guy is acting like a piece of wire. It's not dropping any voltage. All these lights act like a piece of wire because they're not dropping any voltage. And all the voltage would be across the light switch. So if I measured these switches right here, across the switch, I would measure 120 volts. If I measured across these switches right here, I would measure 0 volts. If the switch was good. Now they're going to drop just a tiny bit, but it's not going to be enough to produce any work because there's no such thing as 0 resistance, right? But it's going to be so close. So if I've got a light switch that's dropping 3 volts, then what do you need to do? First of all, it's going to get hot. What do you need to do? You need to change that sucker out. And that's one of the hardest things that is, if I measure across a good fuse, I've got a circuit that's got voltage applied to it. If I measure across a good fuse, how much voltage should it drop? Practically none. It's going to drop a little because this guy definitely got resistance, but it's very, very low because how does it blow? How does it melt? Well, you got to have watts, right? You understand? So to get watts, you got to have V times I. It's just that the wattage is very low. So yeah, fuses will drop a voltage, but it's going to drop very, very little. So I might have a fuse that's rated at 600 amps, and it might drop 2 volts, but it's going to be running a 600 volt supply, right? You understand? So if a fuse drops 2 volts, I'm still getting 658 volts to my load. There's not going to be a difference enough to cause any problems. So fuses will drop. Switches don't drop hardly anything if it's a good switch. When they're what? Fuses, and you'll have that. I'll put this on the test. We got How many people in this class? We've got 9 people in this class. I'll put on a test. I say, okay. I measure 0 volts across fuse. I say, is it good or bad? And I bet you somebody in this class is going to say it's bad. With power of light. I measure a fuse with an ohm meter. How many ohms should a fuse have with an ohm meter? Should have almost none, right? You understand? So if you check a fuse with an ohm meter, it should measure pretty close to 0 ohms. I'll put that on the test. I'll say I measure 0 ohms across a fuse. For some reason, we've got in our mind that 0 is bad. I'll put that on the test. Somebody in this class is going to miss it. I could do it all day in DC. I could do it 3 tests in a row. I can put it on a final exam. They got 20 people in the class. Somebody in that class is going to miss it on every test. Those two questions. And I don't know how to teach it, folks. I don't know how to do it. But understand why the entire voltage appears across the open, because everything else is acting like a wire. Why is it acting like a wire? Because there's no current flow to cause them to drop a wire, to drop a voltage. So they don't drop voltage. Because the only way I can get a voltage drop, V is equal to what? I times the opposition. If I have no I have no voltage drop. Pieces of wire don't drop voltage, right? Does that make sense? So they act like pieces of wire. So that 0, that common, comes all the way through all those loads and sitting on this side of the open. The voltage comes all the way through all those loads because they're not dropping, and it sets across the open. So opens are real easy to find. How do you find an open? Yeah, it's major source voltage. So normally what we do is when we're trying to find the open in a ladder diagram, is we just put one of our meter leads on on L2, and then we start. This is what we do. We come over here and put one of our meter leads right there, and we just start jumping through these devices. As soon as I find a voltage, and you're activating these devices, then that's the device that's open. You have to activate the devices, because if you got an open temperature switch, it's going to be open, right? You understand? So you could either jump it out or something like that. So out of U.S. Steel, everybody carries jumpers. So we have these sensors like this. We come over here and measure no voltage there and measure voltage there. It don't really mean the switch is bad, because it's not going to close until it sees a certain temperature. So we'd put a jumper across it, and then if we got voltage across our coil, then and it wasn't activating, that would mean everybody in front of it was what? So 2 things we carried. We carried lockouts and we carried jumpers. Y'all do that, Earl? Carry them jumpers. Gotta have them jumpers. To jump out these devices that are activated by something. But be real careful when you jump stuff out. So you probably need to pull the power on your motors. Pull the disconnects on your motors. So I get over to something like this. And so what I've got is I've got all these relays. And I want to find the contacts for CR1. So how do we know what contacts belong to CR1? They will have the same label. So what I'm up against now is finding all these contacts. Now this is not a very complicated line diagram. But what we do is we use on the right hand side, on the L2 side, there's some yellow numbers over there now. Are they yellow? We call them numerical cross reference numbers. Can you see what those numbers are doing for us? They tell you the line number that those contacts that belong to that relay, where they're located. So I'm over here troubleshooting CR1, and I'm saying, okay, where are these contacts are? Where are these contacts are? Where are these contacts that belong to that relay? Okay, so where they're at? Where are they at? So we say, okay, there's a contact in line number 1. 2. So I come and notice what you do between each line numbers, you put a comma. Now, they don't necessarily put them inside parentheses. The book does, but U.S. Steel didn't put them in parentheses. So I know I can come up here and I can go down to line number 2. Where's the line numbers at? Here. And anything that's horizontal to this number is that line. And this gives people problems too. If they don't see something connected to L2, they don't want to assign it. They don't want to assign it a number. So you're going to do one whole lab. One of the labs that you're going to do at home is you're going to do this. It's going to tell you how to do it. I'm telling you how to do it now, right? One of the labs that you're going to do while we're off is you're going to go back and you're going to assign line numbers. Any horizontal line every horizontal line gets a number. It don't have to go to L1. It does not have to go to L2. So notice here's the number 2. Is there anything connected right there? No. But if we follow this number over, we draw a horizontal line, there is a line right there. So if there's a horizontal line, it gets a number, right? You understand? So it says I've got 1 in line 2. I come over here and find line 2. Okay, I don't have a dot. Well, I keep doing what? Keep moving over, and then I see it. There it is right there. So that contact belongs to CR1. Where's another contact at? Right here. We're following line what? 3. I'll come over here, find line 3, start following line 3 across, and there it is right there. So that contact right there belongs to CR1. Then I know there's another contact in line 4. Now this is kind of strange. I hadn't seen this before until I taught this class. Anytime we put a contact inside line 1, it gets a number 2. So it says I have a contact in what? 4. So here it is. I come down here, find line number 4, and then there it is right there. So all 3 of those contacts are broken. Okay, I come down to CR2. CR2 has a contact where? In line 8. So I come down here, line 8, and I start following it across, and there it is right there. Oh, sorry, Williams. Thank you. Where do we have another contact at? 10. So here we come, find line 10. So now I can even talk to you about this. Okay, I say, okay, everybody look at the CR2 contact in line 10. So what would you do? I mean, it's no second from the top. It's no third one it's look in the middle, right? You understand that? We don't have to do that because these line numbers are assigned. Here's CR3. Where's its contacts at?
7.
Yeah, line 7. There it is. 9. There it is. 11. Now notice M1 has no contact numbers out there. Why? Because it's a motor starter. All its contacts are over in the power circuit. So this does not tell us the contacts that are located in the power circuit. This tells us the location of the circuits in the control circuit. What about this? The lights don't have contacts. Who in this class is going to assign contact numbers to light bulbs? Somebody in this class is going to do it. Somebody's going to do that. Somebody's going to come over here and just throw these numbers out all over the place, and they're not going to understand what these cross-reference numbers are. They're going to come by the light bulb, and they're going to put through 4 or 5 by the light bulb, right? You understand? I'm going to do what? I'm going to mark it off, take off a bunch of points, because light bulbs do not have contacts. What do the numerical cross-reference numbers do for us? It shows us the location of a relay's contacts within the control circuit, not in the power circuit, in the what? So this looks so easy. Is it easy? Yeah. Somebody's going to screw up on this. Yeah. Chris is going to. I guarantee you, this is a small class, but I have never taught a class in motor controls where we'll sit in this thing right here, right? We'll go over this in class, right? Record its integrity, right? You'll do it on the lab. Unfortunately, I don't grade the lab. When y'all turn them in. I just don't have no time. So what I do is I look at the lab, and you mess it on the lab, and you miss it on test. But you're not going to read the instruction on the lab. You're not going to look at the demonstrations on the lab. You're going to go in there and you're going to do this, and you're going to just assign numbers all over the place. What are you going to do? You're going to skip over lines that are not connected to L. Somebody in here is going to skip over line numbers that are not connected to what? L1. And of course that throws your numbering scheme off altogether. I usually don't, I take out points for skipping, but then I look at the numbers, so you don't lose all of them. And they're going to assign contacts to what? Slide notes. Somebody in this class is going to do it. Please. Please prove me wrong. Please. You'll be the first class. And then I can say, I've only had one class. Okay, so what we need to do is normally, so we add another little thing to it. What does it say? How do we identify normally closed contacts? No, on the numerical cross-reference. You're right, over here I identify it with a line through the contact. But what we do over here is we identify it with the cross-reference. So now I not only know if I'm looking for a normally open contact, but I also know if I'm looking for a normally closed contact. So how do we know we're looking for a normally closed contact? We underline normally closed. We underline the line number of a normally closed contact. Yeah, so somebody's going to put light bulbs up here. You can put numbers. You'll underline a few of them too. So when I get down here to M2 now, all of a sudden M2 has I know it's got a contact somewhere because it's got a watt here on the right. It's got a line number. It's underlined. So I know now I'm looking for what? Normally closed. So I go down here in line 12, I'm looking for the contact that has the same label as the relay. M2, normally closed. And what do we do if we have multiple contacts? We separate them with what? Commas. I had somebody last term that they just wrote number 7, 10, and they wrote right beside each other. So I had to figure that it wasn't 710, right? Okay, so that's line numbers. Does anybody have problems with line numbers? Does anybody have problems with numerical cross-reference numbers? Anything we need to talk about this?
Just one quick question. So we don't have a cross-reference number for M1 or M3 because we don't have a
contact in the control circuit.
Okay.
We got a contact in the power circuit. So we don't show contacts in the power circuit. All we show is contacts that are in the control circuit. Okay. We don't use line numbers in the wiring diagram. Go ahead, George.
Line number 6.
See, ain't that neat? So now you can point me to where. You don't have to say the third line from the top or the fifth, and you say, okay, line number 6. So we know exactly. We're going to come up here and we're going to examine line number 6. So here's line number 6 right here. So anything down this line could be line 6. Okay, now I ask you a question.
Why is the other line number 7 that is under line number 6?
Okay, we just got through talking. Any horizontal line, every horizontal line gets a number. It does not have to go to L1 and it does not have to go to L2. So when I look right here, what do I see? What position is this? Is this vertical or horizontal? Okay, so that gets a line number. Well, where are line numbers at? Line numbers are not right here. Line numbers are always on the left side of L1. So if I follow this guy right here over, this right here is line 7 right there. Because it's a horizontal line. So every horizontal line gets a number. Does the horizontal line have to go to L1? Does the horizontal line have to go to L2? No. If it's a horizontal line, it gets a number. Right? You understand? So now I'm trying to talk about that normally open contact. I said, everybody look at line 6. Well, I was looking at line 6. Well, that normally open contact is not in line 6. It's in line what? 7. Now, if you'd have said, look at line 7, I would have done what? I would have just took 7. I said, well, there's no connection to L1. Well, I would just start following it across until I find the actual contact that belongs to it. So that contact wasn't in line 6, it was in line 7. So every horizontal line gets a what? Number. It does not have to go to L1. It does not have to go to L2. This is very simple. If we look at the U.S. steel prints, we're going to have a lot of horizontal lines that never go back to L1. So I might have 4 horizontal lines. They all belong to the same rung. And I say, okay, look at line 6. And it's not line 6. It's down here somewhere, right? You understand? Then I'm going to have to go, okay, let's look at line 6 and count down three lines. You know, so every horizontal line gets a what? Gets a number. You okay, George? And that's the same thing true over here. So I come over here and I see a 2. Well, where's the line that belongs to 2? There's not a dot right there. Well, there's a line somewhere, so what do? Yeah, I just start following horizontally, and here's line 2 right here, right there. So here I come up here, this says this is in line 12. And this is what you're going to do. This is what somebody in this class is going to come down here on this thing right here, and they're only going to number lines that hit L1. So you're going to come down here, and somebody in this class is going to do this. And you're going to come down here, and you're going to go. I think I got some. Do I have something to draw with? Yeah. So you're going to go 1, 2, 3. You'll skip over that. 4, 5, 6, 7, 8, 9, and 10, and you done screwed up. Now I can't even talk about this contact right here because it don't have a what? Don't have a line number. Somebody in this class is going to do that. You got in your mind to get a line number, it's got to go to L1. You got in your mind to get a line number, it's got to go to L2. So I could come over here and do this. And put another relay. I got to put a load in there, right? I have a short circuit. Well, I've added another line number, so I would follow this over and give it a number, right? So to get a line number, it don't have to go to L1, it don't have to go to L2. All we got to do is have what? A horizontal line. But somebody would miss this right here because it don't come over here. So somebody in this class is going to do, at least one of you, probably more than one, is you're going to come over here on L2 and you're going to number all the lines that touch L1. And of course you're going to miss. These guys are working a lot of fun. You're going to have a lot of contacts. You're going to have a lot of lines in your lab book. And the problem is the lab book tells you exactly how to do it. They give you an example, and you still turn around and mess up on it. And please make me wrong on that. I would love that. Okay. So now I got line numbers. I've got cross-reference numbers. So now it makes the print easier to hook up. But I got to hook this dang thing up. Now in cars, what do they use to indicate the wires? They give them color codes. When you get out to a big plant, they don't use a lot of colors. Because if they got to buy a spool of red, a spool of green, a spool of black, a spool of orange, they don't like doing that, you know. If you went to work out of U.S. Steel and you got into control circuit, you're going to find all black wire. So they use 1 gauge wire, right, because it's the control circuit, and they give it the same color. So that means they buy the only place you're going to run into colored wire is in cables, where you buy the cable, and the cable has different color wires. Now, why do they do that? Well, it saves them tons of money, right? So, oh my goodness, we run out of red. Well, they don't have to run. All they got is what? Black. So what do? How do they identify the wires? Well, they give them numbers. So we have wire numbers. And then what we do at the terminal board, right there where the terminal comes in, we put a label on it that says this is line number 53. So they don't number on the airplanes. On the airplanes or the military airplanes, they actually put the line number the wire number every 6 inches. And in an airplane, the planes I worked in, all the wires were white. They were white jackets. But they put the wire number every 6 inches. And it's actually printed onto onto the wire. But in industry, you're not going to find wire numbers every 6 inches. You're going to find, only place you're going to find those is at terminals. Is that right, Rick?
If you're lucky sometimes.
If you like to add more off, but they're usually pretty good. Not that somebody's came in and pulled new wire and not put the terminals back on. Or a wire's broken, they've cut the terminal off and they cut the line number off with the terminal. And they don't put them back on there. We had a big old fish finder we were working on. And the sensor, the loop it was for finding motors in the river. So it had a big old, a couple of big old ropes on it, and you dropped it off the back of the boat, and it was a metal detector, and what you did is you slid it along and you found these motors. People drop motors off their boats all the time, believe it or not, especially around the peak. And it wouldn't work. And it was vacuum tube. The vacuum tubes run off about 250 volts, and all the wires in the whole thing was brown. And the thing would pick up WVOK up here perfect. You know, WVOK, the big AM station, we could listen to that, but it wouldn't work. But man, we had the hardest time working on that thing. So what we would do is we'd throw the big old loops out there on the ground, and the guy that owned it, we had it moving trash cans in and out of the loop. And we told everybody, what's he doing out there? He says, he's majoring in sanitation engineering. True story. Poor old Alfred. He's still one of my friends. Huh? Yes, we can take time out. Take time out. And we'll look at wire numbers. And then we'll look at as soon as I sign this number right here, then everything connected to L1 gets that same number. So that's line number 1. I mean wire number 1. Y'all watch me. I don't want to say that. Okay? So all these are wire. Y'all understand? Then I get over here. So now I start up here on rung 1. I go 1. Anytime you go through something, it gets another number. So I go through a push button. So this is line number what? 2. Okay? This wire is line number 2. So what I would is on this terminal I would have a 2 wrapped around the wire. Over here I'd have a 2 wrapped around the wire. But what are you going to find? These wire numbers are only going to be on the terminal blocks. Now I've gone through. As soon as I go through CR, I sign this right here, line number what? 3. Everything connected directly to L2 gets the same number. If they are electrically the same, so that means if I come over here and I put a meter right here, a voltmeter right there, and I put a voltmeter right there, what's that voltmeter going to measure? It's going to measure 0 volts. There's no R. It's nothing but wire. So they are electrically the same. So that means if I want to find L2, if I assign L2 all these different numbers, then I'm going to have a problem. But if L2, every wire that is connected to L2 is assigned the number 3, then where can I hook on to L2 at? Anywhere I see the number what? 3. I could hook on it down here. I could hook it on anywhere I see the number 3 on any terminal board, anywhere on the system. If I see the number 3, that is L2. If I see the number 1, that is L1. If I wanted to measure the voltage between L1 and L2, I don't have to go to the transformer, right? You understand? Where can I go? Well, all I got to do is find the wire number what? 3 and the wire number 1 and measure across it. Every time you go through something, it gets a different number. So let's look at this guy right here. This is 1. I've already used 4. This is still 3, right? You understand? Here's 1. I go through something. This is what? 5. What would be this number right here? This is going to be 5. Why? It's a different wire. It's electrically the same. So if I wanted to get across this limit switch, I don't have to get across that limit switch. I'm going to find L1 somewhere, and I'm going to find wire number 1, and I'm going to find wire number 5. You're going to say, wait, that's across the pressure switch. I don't care. It's also across the limit switch, right? You understand? This guy here kills people right here. Assign it. Here's a relay. Right on this side I have 6. I go through the relay. I've gone through something. This gets another number. When I come through this is an overload. This gets a number, but that number's already been assigned what? 3. For L2. For wire number 3. So every time you go through something, it gets a what? It gets another wire number. If it's connected together, they have the same wire number. So now I know how to wire these things up, right? So what I would do while I'm wiring these things up, so they're showing here's my push button, right? This would be what? This would be line 1, wire 1. This would be wire 2. Then it's going to come into a box, a device box. It's going to go through some conduit. And over here I've got a 1 and a 2. So where would this one right here hook up to? Well, it's going to hook up to L1. Where would the 2 hook up to? It's going to hook up to this terminal right here. That's on the relay. So that's wire numbers. Any questions on wire numbers? Each wire number in a control circuit is assigned a reference point on a line diagram to keep track of the different wires that are connected. These components to the components in the circuit. And man, you get into industry. If you work on a motor control circuit in the industry, odds are the only color-coded wires you're going to see are in cables. All these other wires, they're going to be in these little plastic wire troughs. They use them to arrange them. We got some in here somewhere. They're going to come poking out, and they're going to hook up to a terminal board. At the terminal board should be the wire number. I've seen it 2 different ways. They put the number on the actual terminal block itself, or that's good. But I like it to put it on the wire. So you can buy these wire numbers, and they come on a little spool. You break them and you wrap them around, and you got 0 through 9. And you just wrap, if you got wire number 100, you just find 1 and 2 zeros on there. Wrap them around there, and they last real good. That's like that. On the airplane wires, they literally put those numbers on the wires before they put them in the wire. So, but those are real easy. So you got a ball of wire, all white, they're all the same gauge. It's all that big right there. They're all bundled together. And all you got inside that plane is white wires. You ever get inside an airplane and look at the amount of wires you have in it. I mean, just big old bundles, especially when you get up in the cockpit. We always love that drive coming in. Smell smoke in cockpit. You probably got 200,000 wires coming into the cockpit. Smell smoke in cockpit. And for some reason, when they smell smoke in an airplane, they get upset about that. They want to land real fast. The cockpit had a smoke vent in it, by the way, so they could pop open a vent where they could shoot a sextant up there too. But they did that too. They'd pop that thing to. We had one of our friends, so Fuick, he used to get out there and pressurize the plane, so you couldn't get in the door, and it'd go up in the cockpit and smoke pot. And it'd pop open the smoke vent up in the cockpit, and it's pressurized, so it's blowing smoke out of there. It didn't leave any odor. He was a unique individual. We was over in Thailand, and Fuick wanted to send his wife a bunch of pot, and he just poured it up and put it in an envelope and sent it off. And of course, they delivered it and arrested his wife and threw him in jail. And they came up to old Fuick, and he says, I leave my mail open up on my desk all the time. Anybody could have put that in there. So Fuick got out of it, and his wife was in jail. So it was true story. These are called manufacturer numbers. Manufacturer numbers are not assigned by you. Manufacturer numbers are assigned by who? The manufacturer. So when I come up here and I buy this relay right here, and we can look at all these devices, and they're going to have a set of manufacturer numbers on them. Of course, these are actually on the device, but I don't know if you can see 1, 2, 3, L2, L1, L3. So these are the actual manufacturer numbers on the device. And of course, what they do on us is just bring the manufacturer numbers out to a terminal board, right? So when you buy a device, all the terminals are going to be numbered or labeled. You do not assign those manufacturer numbers, but you have to know the manufacturer numbers to do what? To know how to wire them. So you might, this is a 5, but wire number 53 might be coming into terminal 5. Well, you assigned the 53, right? Somebody in your group or whoever developed the wiring diagram, they assigned the 53. Who assigned the 5? The manufacturer of this relay. So all these devices have manufacturer numbers on. Sometimes they'll draw it on a little print on the side of the device. This, of course, doesn't do that. So that's manufacturer numbers. Everybody okay on those? Yes or no?
Do they affect wire numbers?
No. You assign the wire numbers. Okay. So, huh?
As long as the point of reference on where we're supposed to be wiring.
Yeah, so we bring, and this is what we was talking about. So my wire number might be 53. But it might hook up to terminal 5 on the device. So terminal 5 was not assigned by me, it was assigned by the manufacturer. Okay. When I come into mine, or they set up, when they come in and the engineers design my control circuit, they assign the wire numbers. The manufacturer of the components, so I go out and I buy a switch. You know, the switch is going to come with numbers on it. I'm trying to see if there's got any, this guy usually don't need numbers because there's so little. Everything is visibly available to it. No, they got a C on here for coil, so they got a C or coil, and they don't have numbers on the other thing. But here's this relay right here. So this is L1, but they also give it to what? Number 1. This is L2. They also call it terminal 3. This is L3, also referred to as terminal 5. So that means I don't have to use this to control L1, L2, L3. I could actually use it as a number, right? Understand? Then I come down to this side, and they got what? 2 and T1. So that would be this contact right here. This is T2 or 4. This is T3 or 6. Now, who did these? Yeah. And even if I look down here, we see this has 2 contacts on it. It says one in the bottom, one in the top. So they didn't put, so this bottom would be terminal, this would be 14. This right here would be 22. Over here, the bottom terminal would be right down here. This would be 13, and the top terminal would be 21. Now, how did they get on there? The manufacturer assignment. So when I wire, I'm going to say, okay, this wire number 53, needs to go to terminal 5 on this relay. So wire number 53 would hook up to that manufacturer's number. Manufacturer numbers are assigned by the manufacturer. They have no idea, odds are, you know, where can we put this thing at? We sell it all kind of places. They don't have any idea what line number you're going to use or what wire number you're going to use. They have no idea. And of course, that gets confusing sometimes because you got 2 numbers to deal with. You got wire number 174 connected to terminal 5. Right? You understand? This gives us problems in digital all the time too, where we have pin names and pin numbers. And sometimes the name of the pins are numbers. So you'll have the name of the pin is 0, but it might be pin 3, and that gets people confused all the time. Or it might be, the pin name might be 4, but it might be pin number 6, right? You understand? And that's the same thing we have here. So wire numbers are how we identify the wires. Manufacturer numbers are how we identify to connect to that device, right? Okay? So this is a very important document that we're handing out now.